Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. The vastness of space holds countless wonders, but few as intriguing as the massive intergalactic traveler currently on a collision course with our home galaxy. High above the plane of the Milky Way, a colossal cloud of hydrogen gas hurtles through the void at over 40,000 miles per hour. This cosmic behemoth, known to astronomers as the Smith Cloud, spans an incredible 11,000 light-years across and contains enough gas to form millions of stars like our Sun. First discovered in 1963 by doctoral student Gail Smith using the Dwingaloo Radio Observatory in the Netherlands, this mysterious object has puzzled astronomers for decades. Unlike most objects in the universe that we observe from Earth, the Smith Cloud isn't moving away from us. It's coming straight toward the Milky Way's disk, projected to collide with our galaxy in approximately 30 million years. The cloud itself is invisible to the naked eye, and even to most optical telescopes. It exists primarily as neutral hydrogen gas, detectable only through radio astronomy. When scientists point their radio telescopes toward the constellation Aquila, they can map the cloud's enormous structure, stretching across 15 degrees of sky, equivalent to 30 full moons lined up edge to edge. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. What makes the Smith Cloud particularly fascinating is its trajectory. Unlike random interstellar gas clouds, it appears to be on a specific path that suggests it has already passed through the disk of the Milky Way once before. Using data from the National Radio Astronomy Observatory's Green Bank telescope, astronomers have reconstructed its path backward in time. Their calculations reveal that approximately 70 million years ago, the cloud likely passed through the outer regions of our galaxy's disk. This peculiar behavior raises profound questions. What is the Smith Cloud? Where did it come from? And what might happen when it inevitably crashes into our galaxy again? For decades, astronomers believed the Smith Cloud was a failed dwarf galaxy, a small collection of stars and gas that never quite managed to form a proper galaxy structure. Others suspected it might be a pristine intergalactic cloud, untouched by star formation and containing only the primordial elements from the early universe. Recent observations have dramatically shifted our understanding. In 2015, astronomers using the Hubble Space Telescope made a groundbreaking discovery about the cloud's composition. By examining the ultraviolet light from distant quasars shining through the cloud, they detected significant amounts of heavy elements like sulfur, elements that can only be created inside stars. This chemical signature provides compelling evidence that the cloud originated within our own galaxy, not from beyond. The emerging picture is that of a galactic fountain, gas that was once ejected from the Milky Way's disk by powerful stellar, winds or supernovae explosions, only to rain back down millions of years later. It's part of a grand recycling process that operates on timescales and spatial scales almost incomprehensible to the human mind. As the massive cloud continues its journey toward our galactic neighborhood, it offers a unique natural laboratory for understanding the complex dynamics of galaxies. The Smith Cloud represents not just a fascinating cosmic phenomenon, but a window into the past and future of our own galactic home. To comprehend the extraordinary nature of the Smith Cloud, one must first understand its immense scale. This colossal structure contains enough hydrogen gas to form over 2 million stars the mass of our Sun. If visible to the naked eye, it would span an area of sky approximately 30 times the width of the full moon, despite being tens of thousands of light years away. The cloud is primarily composed of hydrogen gas in various states. Most exists as neutral atomic hydrogen, HI, detectable through its emission at the 21-centimeter wavelength, a spectral line that has become fundamental to radio astronomy. This specific wavelength arises from the quantum spin-flip transition of hydrogen atoms and allows astronomers to map the cloud's structure with remarkable precision. But the Smith Cloud isn't merely a uniform mass of gas. Radio observations reveal complex internal structures regions of varying density, filaments and shells that suggest a turbulent history. These features resemble ripples in a pond, potentially indicating past interactions with the Milky Way's gravitational field, or even collisions with smaller gas clouds during its journey. When astronomers measure the cloud's velocity, they discover another remarkable property. It's moving at approximately 73 kilometers per second, roughly 45,000 miles per hour, with respect to the rotation of the Milky Way. This incredible speed means that when it eventually collides with our galaxy's disk, the impact will trigger significant compression of the gas, potentially igniting a new era of star formation in that region. The Smith cloud also possesses a magnetic field, detected through polarized radio emissions. This magnetic structure serves as a protective shield, helping the cloud maintain its integrity during its journey through the galactic halo, the diffuse, hot gas surrounding the Milky Way's disk. Without this protection, the cloud would likely have been torn apart or evaporated long ago. Perhaps most intriguing is the cloud's chemical composition. Initial assumptions suggested it might consist of pristine gas from the intergalactic medium, containing only hydrogen and helium created in the Big Bang. However, spectroscopic observations by the Hubble Space Telescope revealed the presence of heavier elements, specifically sulfur, at approximately 30% of the abundance found in the Sun. This metallicity measurement, as astronomers call the proportion of elements heavier than helium, provides crucial evidence about the cloud's origins. The presence of these heavy elements indicates that the gas has been processed through at least one generation of stars, which transform hydrogen and helium into heavier elements through nuclear fusion and subsequently release these materials through stellar winds or explosive deaths. The cloud's leading edge exhibits signs of compression and heating, much like the bow shock that forms in front of a boat moving through water. This compression creates a slightly higher density region that glows more brightly in radio observations. Behind this leading edge, streams of gas trail off, creating a comet-like appearance that points back along its trajectory. Temperature measurements across different regions of the cloud vary considerably. The outer edges, where the cloud interfaces with the hot galactic halo, reach temperatures of several thousand Kelvin. In contrast, the denser interior regions remain cooler, with temperatures of just a few hundred Kelvin. This temperature gradient creates perfect conditions for the formation of molecules like hydrogen, H2, which require cooler environments to exist. As astronomical instruments grow more sophisticated, our understanding of the Smith cloud's structure continues to evolve. Each new observation reveals additional layers of complexity in this gigantic celestial traveler, challenging our models and expanding our knowledge of the dynamic processes that shape galaxies like our own. The question of where the Smith cloud originated has puzzled astronomers since its discovery. Initially, scientists proposed three main hypotheses. It could be a primordial gas cloud from outside our galaxy, a failed dwarf galaxy, or material ejected from the Milky Way itself. Each origin story carried profound implications for our understanding of galactic evolution. For decades, the prevailing theory suggested the Smith cloud was an example of a high-velocity cloud, HVC, one of many mysterious gas clouds observed, moving at high speeds relative to the Milky Way's rotation. Many HVCs are thought to be primordial material falling into our galaxy for the first time, remnants from the formation of the local group of galaxies. However, the 2015 Hubble observations dramatically reshaped this narrative. The discovery of significant sulfur content in the cloud, roughly 30% of the Sun's metallicity, indicated that the gas had been processed through stellar nucleosynthesis. Stars forge heavy elements in their cores and distribute them when they die, meaning this gas had already existed in proximity to stars. This chemical signature pointed toward a new explanation. The Smith cloud is likely part of a galactic fountain process. In this model, explosive events in the galaxy's disk, such as clustered supernovae from massive star formation regions, can eject tremendous amounts of gas perpendicular to the galactic plane. This ejected material doesn't escape the galaxy's gravitational pull, but instead arcs through the halo and eventually falls back to the disk, completing a cycle that can take tens of millions of years. Computer simulations tracing the cloud's trajectory backwards support this fountain hypothesis. These models suggest the Smith cloud originated in the outer regions of the Milky Way's disk approximately 70 million years ago in the Perseus arm, about 15,000 light-years from the galactic center. The cloud was likely propelled upward through the disk, perhaps by multiple supernovae explosions occurring in a stellar nursery. Yet mysteries remain. The cloud's extraordinary mass, estimated at over 1 million solar masses, far exceeds typical fountain processes observed elsewhere in our galaxy. This anomalous size suggests either an exceptionally energetic ejection event or additional factors contributing to its formation. One intriguing hypothesis proposes that the Smith cloud might contain dark matter, the invisible substance that makes up approximately 27% of the universe. If a significant dark matter subhalo surrounds the cloud, it would provide additional gravitational binding, explaining how such a massive gas structure could remain relatively intact during its journey through the galactic halo. This dark matter component would act as a protective cocoon, preventing the gas from being stripped away by interactions with the surrounding medium. Another possibility involves the galaxy's central supermassive black hole. Periodic activity from this black hole can generate powerful outflows, capable of expelling enormous amounts of gas. Could the Smith cloud represent material ejected during a particularly active phase of our galaxy's central engine? The debate over the cloud's origins isn't merely academic. Understanding the Smith cloud's history provides crucial insights into the Milky Way's evolution, the cycling of materials between galactic components, and the processes that regulate star formation over cosmic timescales. Researchers continue investigating these questions using increasingly sophisticated instruments. The 500-meter Aperture Spherical Telescope, FAST, in China, and the upcoming Square Kilometer Array, SKA, promise unprecedented sensitivity that may reveal fainter structures associated with the cloud, potentially providing additional clues about its formation. As astronomers gather more data, the Smith cloud's origin story continues to evolve, a testament to the dynamic nature of scientific discovery and our ever-deepening understanding of the complex processes that shape our cosmic neighborhood. In approximately 30 million years, the Smith cloud will complete its arcing trajectory and collide with the Milky Way's disk in the constellation Sagittarius, between 15,000 and 45,000 light-years from the galactic center. This cosmic collision, while seemingly catastrophic, promises to be a creative rather than destructive force in our galaxy's evolution. To understand the impending impact, astronomers use sophisticated computer simulations that model the complex interactions between the cloud and the galactic disk. These simulations incorporate data on the cloud's mass, velocity, density distribution, and magnetic field structure to predict how the collision will unfold across millions of years. When the cloud strikes the galactic disk, it will generate a tremendous shockwave as gas moving at over 40,000 miles per hour compresses the relatively stationary material in the disk. This compression will create perfect conditions for the formation of molecular hydrogen, the essential building block for new stars. The collision region will likely experience a dramatic increase in density, triggering gravitational collapse within the gas and potentially igniting a substantial episode of star formation. Calculations suggest this single event could spawn up to 2 million new stars, with masses ranging from tiny brown dwarfs to massive short-lived giants. This stellar baby boom would appear as a distinctive cluster, with the stars sharing similar ages and chemical compositions, providing future astronomers with a clear record of this cosmic collision long after it occurs. The impending collision also offers a unique window into understanding how galaxies grow and evolve. Throughout cosmic history, galaxies like the Milky Way have grown not just through internal star formation, but through the accretion of external material. The Smith cloud represents this process in action, a substantial addition of fresh gas that will fuel new generations of stars and contribute to our galaxy's ongoing evolution. The collision zone won't just create stars. The intense radiation from newly formed massive stars will ionize the surrounding gas, creating vibrant emission nebulae similar to the Orion Nebula, but potentially spanning hundreds of light years. These colorful cosmic clouds would be visible for millions of years before gradually dissipating as the massive stars explode as supernovae. These supernovae will further enrich the region with heavy elements, continuing the cycle of stellar birth, death, and rebirth that has characterized galactic evolution for billions of years. In essence, the Smith Cloud collision represents a microcosm of the processes that have built galaxies throughout cosmic history. While the collision itself remains millions of years in our future, astronomers have identified several other high-velocity clouds that may represent similar phenomena at different stages. The complex of hydrogen clouds, known as Complex C, for example, shows evidence of currently interacting with our galaxy's disk, providing a preview of what might happen when the Smith Cloud arrives. The upcoming collision also raises intriguing questions about similar events in our galaxy's past. Could previous impacts from gas clouds like the Smith Cloud explain some of the distinctive stellar populations we observe in the Milky Way today? Certain star clusters with unusual chemical compositions or orbital characteristics might be the stellar fossils of ancient cloud collisions. By studying the Smith Cloud's approach, astronomers gain insight into the galaxy's past, present, and future. Each observation adds another piece to the puzzle of galactic evolution, a story written across billions of years and hundreds of thousands of light years, yet increasingly legible through modern astronomical techniques. As we track this enormous cloud on its collision course with our cosmic home, we're witnessing not an impending disaster, but rather an essential process in the life cycle of galaxies, a process that has likely occurred countless times before and will continue long after our civilization has faded into cosmic history. The Smith Cloud represents just one component in an intricate galactic recycling system, a perpetual exchange of material between the Milky Way's disk, where stars form and live out their lives, and the surrounding halo of diffuse gas. This cosmic circulation system operates on timescales of millions to billions of years, governing the evolution of our galaxy and others like it throughout the universe. At the heart of this recycling process lies a delicate balance of forces. Gravity continually pulls gas inward toward the galactic disk, while various energetic processes, supernova explosions, stellar winds, radiation pressure, and occasionally activity from the central supermassive black hole, push material outward. The result is a dynamic equilibrium that regulates star formation and controls the galaxy's long-term development. Astronomers classify this circulation into several distinct cycles. The galactic fountain represents the smallest scale, with gas ejected only a few thousand light-years above the disk, before raining back down within tens of millions of years. The Smith Cloud exemplifies a more extreme version, reaching heights of over 40,000 light-years above the plane and taking more than 70 million years to complete its cycle. On even larger scales, some gas can be ejected with sufficient velocity to escape the galaxy entirely, enriching the intergalactic medium with heavy elements. This expelled material may eventually be recaptured by the same galaxy or incorporated into other galaxies, spreading the products of stellar nucleosynthesis throughout the cosmos. For decades, theorists have recognized the importance of these gas flows for regulating star formation. Without this circulation system, galaxies like the Milky Way would likely have converted all their gas into stars billions of years ago, becoming red and dead collections of aging stellar populations. Instead, the constant recycling of gas, combined with the slow accretion of fresh material from intergalactic space, maintains a steady supply of star-forming fuel. Recent observations with sensitive radio telescopes and ultraviolet spectrographs have revealed the extent of this circulation system. Around the Milky Way, astronomers have detected a vast reservoir of multi-phase gas, ranging from cool, dense clouds like the Smith Cloud to hot, diffuse plasma at millions of degrees Kelvin. This circumgalactic medium contains as much mass as all the stars in the galaxy combined, serving as both a repository for ejected material and a source of fresh gas for future star formation. The Smith Cloud's chemical composition provides direct evidence of this recycling process in action. Its metallicity, approximately 30% of solar values, matches what astronomers would expect from material ejected from the outer galactic disk several tens of millions of years ago. As this material returns to the disk, it will mix with existing interstellar gas, slightly diluting the heavy element content in some regions while providing fresh fuel for new generations of stars. The cloud's journey also illuminates how the galactic magnetic field participates in this recycling system. As gas rises from the disk, it carries magnetic field lines along, stretching and reconfiguring the galaxy's magnetic architecture. When this material falls back, it helps to maintain the coherent magnetic field structure observed throughout the Milky Way, a field that influences everything from star formation to cosmic ray propagation. Advanced computer simulations of galaxy evolution now incorporate these complex feedback mechanisms, modeling how the transfer of energy, momentum, and enriched material shapes galaxies over cosmic time. These models suggest that without such robust circulation systems, galaxies would look radically different, either burning through their gas too quickly or accumulating too much mass in their central regions. By observing the Smith cloud and similar structures around other galaxies, astronomers are piecing together a comprehensive understanding of these galactic ecosystems. Each observation confirms that galaxies are not static structures, but dynamic, self-regulating systems in constant flux, cosmic recyclers that have refined their processes over billions of years. Studying an invisible cloud of hydrogen gas hurtling through space presents formidable challenges to astronomers. The Smith cloud emits no visible light, contains no stars, and can only be detected through specialized techniques that have evolved dramatically since its discovery in 1963. Gail Smith first identified the cloud using the Dwingaloo Radio Observatory, a 25-meter telescope in the Netherlands that was state-of-the-art for its time. This pioneering observation detected the characteristic 21-centimeter emission line of neutral hydrogen, a spectral fingerprint created when a hydrogen atom's electron flips its spin direction. This subtle quantum transition produces radio waves that can penetrate the dust and gas, obscuring our view of many regions of the galaxy. For decades following its discovery, the cloud remained poorly characterized due to the limited sensitivity and resolution of early radio telescopes. The breakthrough came in the early 2000s with the Green Bank Telescope, GBT, in West Virginia, a 100-meter dish that remains one of the world's most sensitive radio instruments. The GBT's observations revealed the cloud's true extent and structure with unprecedented clarity, mapping its filaments, density variations, and distinctive cometry shape. These radio observations provided crucial data about the cloud's mass and motion, but could reveal little about its chemical composition. For that, astronomers needed to deploy a different technique, absorption line spectroscopy. By observing how the cloud absorbs light from background sources like quasars, researchers could determine which elements are present in the gas. The Hubble Space Telescope's Cosmic Origins spectrograph proved instrumental for this task. In 2015, astronomers used Hubble to study ultraviolet light from distant quasars passing through the Smith cloud. These observations detected the distinctive spectral signatures of elements like sulfur, silicon, and aluminum, heavy elements that could only have been created inside stars. This key discovery shifted understanding of the cloud's origins, pointing toward an origin within our own galaxy rather than from intergalactic space. Mapping the magnetic field structure presented another observational challenge. Astronomers tackled this by measuring Faraday rotation, the way magnetized plasma rotates the polarization angle of radio waves passing through it. Combined with observations of the cloud's own synchrotron emission, these measurements revealed a surprisingly organized magnetic field that helps maintain the cloud's coherence during its journey. One persistent challenge involves determining the cloud's precise distance, which remains uncertain despite decades of study. Unlike stars, gas clouds offer few reliable distance indicators. Astronomers must rely on models of the galaxy's gravitational field combined with the cloud's observed velocity to triangulate its position. This uncertainty affects estimates of the cloud's mass, size, and even its future trajectory. technological innovations continue to enhance our understanding of the Smith Cloud. The Arecibo Observatory, before its unfortunate collapse in 2020, provided detailed spectroscopic measurements that revealed variations in the cloud's velocity structure. The Carl G. Jansky Very Large Array (VLA) in New Mexico has mapped the cloud at higher resolution, revealing intricate filamentary structures that suggest ongoing interaction with the surrounding galactic halo. Future observatories promise even greater insights. The upcoming Square Kilometre Array (SKA), with its unprecedented sensitivity, will detect fainter gas structures that may connect the Smith Cloud to other high-velocity clouds or to the galactic disk itself. The James Webb Space Telescope could potentially detect infrared emission from the cloud's leading edge, where compression might be sufficient to form small amounts of molecular hydrogen that emit in the infrared spectrum. As observational capabilities advance, new questions emerge. Does the cloud contain significant amounts of molecular gas hidden from current detection methods? Are there stars forming within its densest regions? Does it harbor its own population of dark matter? Each technological breakthrough brings us closer to answering these questions, transforming our understanding of not just the Smith Cloud, but of the complex gas dynamics shaping galaxies throughout the universe. The Smith Cloud's journey toward our galaxy represents just one example of a phenomenon that occurs throughout the cosmos. By placing this spectacular gas cloud in its broader astronomical context, we gain perspective on the universal processes that drive galactic evolution across space and time. Similar clouds have been observed around other spiral galaxies, suggesting that this gas recycling process is common throughout the universe. The nearby Andromeda Galaxy, M31, shows evidence of multiple high-velocity clouds in its halo, while observations of more distant galaxies reveal extensive networks of gas streams, clouds and filaments extending tens of thousands of light-years from their disks. These observations confirm that galaxies are not isolated islands in space, but rather open systems, constantly exchanging material with their surroundings, accreting fresh gas from the cosmic web, and sometimes losing enriched material to the intergalactic medium. This continuous gas exchange influences everything from a galaxy's star formation rate to its chemical evolution and even its morphological development over billions of years. The Smith Cloud also provides insight into a long-standing puzzle in galactic evolution known as the missing baryon problem. Cosmological models predict that typical galaxies should contain far more ordinary matter, baryons, than we observe in their stars, dust, and visible gas. The detection of massive gas reservoirs like the Smith Cloud in galactic halos helps account for some of this missing material, though significant quantities still remain unaccounted for. Looking ahead, astronomers continue developing more sophisticated tools to study these phenomena. The previously mentioned Square Kilometre Array, when completed in the late 2020s, will revolutionize our ability to detect and map hydrogen throughout the universe. This international facility, spanning South Africa and Australia, represents a 100-fold improvement over current radio telescopes, potentially revealing thousands of Smith Cloud analogues around nearby galaxies. In space, next-generation ultraviolet telescopes will extend the work begun by Hubble, providing detailed chemical fingerprints of circumgalactic gas clouds through absorption line studies. These observations will help classify different cloud populations based on their origins, distinguishing between recycled material, like the Smith Cloud, pristine intergalactic gas, and debris from satellite galaxy interactions. Advanced computer simulations will play an equally important role in future research. As computing power increases, astrophysicists can model gas flows around galaxies with ever greater resolution and accuracy, incorporating complex physics like magnetic fields, cosmic ray transport, and radiative cooling effects. These simulations will help predict the long-term fate of structures like the Smith Cloud with unprecedented precision. The Smith Cloud's eventual collision with our galaxy's disk represents more than just an interesting future astronomical event. It embodies the perpetual processes of destruction and creation that govern cosmic evolution. the same fundamental cycle that has transformed primordial hydrogen and helium into the rich chemical diversity we observe today, including the elements that make up Earth and life itself. When the cloud finally impacts the Milky Way's disk 30 million years from now, any intelligent observers in that region will witness a spectacular astronomical phenomenon: new star formation, brilliant emission nebulae, and perhaps even the birth of planets that might one day harbor life. Though humans will likely never witness this collision, our scientific understanding allows us to project forward and envision these future cosmic events. The story of the Smith cloud reminds us that the universe remains in constant flux. Galaxies are not static entities but dynamic, evolving systems, shaped by processes operating across an enormous range of scales, from the quantum transitions that produce hydrogen's radio emission to the vast gravitational forces that guide intergalactic gas clouds across hundreds of thousands of light years. As our observational capabilities and theoretical understanding continue to advance, we can expect many more discoveries about the complex gas dynamics shaping our galaxy. The Smith cloud represents not an endpoint, but a beginning, one thread in the vast cosmic tapestry that astronomers continue to unravel as we expand our exploration of the universe and deepen our appreciation for the intricate processes that have, over billions of years, made our existence possible.